Good afternoon. I'm Aaron Powell. Today I'll present our final project for doing data science, predicting tip amounts in New York City yellow taxis using 2025 trip data from the New York City Taxi and Limousine Commission, while uncovering meaningful insights into rider behavior. Follow along while I take you through the data science pipeline: import, tidy, transform, model, visualize, and communicate, plus a Shiny app with natural language interaction. Let's dive in. Our dual objectives are insights and predictions. I've developed focused insights on taxi rides from airport locations and temporal patterns, while building a linear regression model to forecast taxi trip amounts from trip characteristics. All code and data processing is live in GitHub. So, how much will a rider tip? And can we learn about tip behavior from the characteristics in the data? The official 2025 Yellow Taxi trip records have approximately 48.7 million trips. Rather than forcing the entire dataset through a computer and waiting, let's work with a representative sample that allows high quality, reproducible analysis. We begin by ingesting the Parquet files efficiently with the Arrow package. A memory efficient random sample of 5,000 rows was drawn and validated against the full population. Summary statistics for tip amount, total amount, and trip distance matched closely, confirming representativeness. Then, we applied tidy data principles from the course to handle blank, missing value, and outliers. We worked exclusively with credit card transactions because cash tips are confounded by manual entry and tax policy. FlexFare shows systematically lower tips, likely due to third-party application behavior. We filtered out unrealistic values such as negative or zero distance trips and fares. Then created indicators for FlexFare rates, surcharges, trips to and from an airport, as well as weekend and trips during rush hours. At this point, we can start engineering practical features such as deriving trip duration in minutes from pickup and drop-off times, average speed of the trip, tip percentages, and the fare per mile. Using these features, we filtered out any clear data errors or outliers not representative of our target population. This focused scope made modeling and insight generation both feasible and meaningful. Now let's check out the insights. We found evidence mean tip amount during rush hours was different than that of others, with an estimated 3% greater tip during rush hours. The mean trip distance was about 17 minutes and encompasses 65% of taxi rides. Naturally, rides below the average time have 32% average lower tip amount than the average tip for taxi rides greater than 17 minutes. This tells us New York City yellow cab riders may derive tip amounts by percentage of the total amount. Our dataset mostly focuses on standard trip rates, which biases our models slightly due to the confounding variables with cash and FlexFare tip amounts we discussed earlier. This box plot highlights location-based differences dictating the rate code used. Trips to and from airports command significantly higher tips, often double or more the standard rate, with higher medians and generally lower zero tip percentages. Standard ride averages have a tip amount of $3.96, while JFK rides jump to roughly $12.87. This pattern likely reflects longer distances, fixed surcharges, and traveler mindset at trip endpoints. Is there a temporal pattern to tips? Mean tip amount vary noticeably across the day, with differences between weekdays and weekends. Overnight and rush hour periods tend to show premiums, while weekend patterns diverge from weekday ones. These effects hold after controlling for distance and fare, suggesting behavioral factors like urgency, nightlife, and fatigue influence generosity. This insight helps drivers and dispatch systems anticipate higher earning windows. Let's look at our prediction models. We built multiple linear regression models using engineered features such as trip distance, trip duration in minutes, pickup hour, rate code ID, rush hour, and interactions, deliberately avoiding total amount to prevent leakage and ensure practical usability. We start with a full model to review coefficients and begin investigating collinear pairs. We use the full model in the simplest yet most predictive model we can build as a reference point for comparing residuals. We'll note how much variance each model explains and begin feature selection. We choose to use a step AIC process to search for the most parsimonious model. Then we compare residuals and investigate collinearity to a customized model with interactions built in. This allows the model to account for changes in the rate code against both trip distance and duration, instead of a flat adjustment. The interactive model explains more and has been better predictive power at the cost of inflated variance. Diagnostic plots confirm our model is mostly robust to linear regression assumptions of linearity, normality, and equal variances. And the winner is our interactive model. The model delivers the most balance, highest adjusted R squared in both our train and holdout test set, comfortable mean absolute error with the best possible root mean squared error. The AIC and BIC scores confirm the model is not overly complex compared to the simplest possible model. We delivered reliable, interpretable tip predictions alongside two clear data-backed insights: higher tips at airports and during specific rush overnight events. These findings are actionable for drivers seeking better shifts, fleets negotiating contracts, and city stakeholders improving service. Everything is fully reproducible via our GitHub repository, and to make the results accessible, we built an interactive Shiny app. The Taxi Tips dashboard includes three main sections: data exploration with filters, an interactive tip predictor, and visualizations of our insights. The standout feature is an Ask the Taxi Driver, a natural language interface powered by a retrieval augmented generation setup grounded in the analysis, model outputs, and project documents. Users can ask plain English questions like, how do tips differ at JFK, and receive responses tied directly to our work. To wrap up, this project reinforces the end-to-end data science process emphasized throughout SMU's Masters of Science in Data Science 6306 Doing Data Science course. From tidy data practices and reproducible workflows with GitHub to linear modeling, assumption checking, and stakeholder-friendly deployment. Thank you for your attention.